Alright, so we are ready to start the next section, and this section is more like a discussion entirely. It's not extremely heavy. We have only one main definition in this section, and that's it. But before that, there are some other things the author has talked about. So the name is the algebra of real valued functions. We have already seen what real valued functions are, and we already in fact know, we have known before starting this text itself. These are functions which look like this. Whose domain is R and range is also R. And in fact, this is not the only kind of real valued function that we know. We in fact also know other functions where the domain is not the entire set of real numbers but some subset. For example, an interval like this, we have already seen these things in calculus. And the author then talks about some examples of functions. Actually, we can consider any functions, but because these are given in the text, so let's just see what they are. For example, we are well familiar with functions which look like this. These are polynomial functions. That is, the rule for the function is given by a polynomial. Or you can also consider a slightly more complicated function like this. Which is a mixture of a polynomial and this exponential function. Or if one wants to be even more complicated, one can consider things like this. And then the author says that these are examples of algebraic functions, which roughly it means that these functions are expressible in terms of x and the basic laws of arithmetic like addition, subtraction, multiplication, division, taking square root, etc. And this notion of algebraic functions will not be explored in detail here in the text. Functions which are not algebraic are called transcendental. Actually, there is a definition, there is a precise definition. It says that such a function f is called algebraic if there exists a polynomial in two variables over the integers. That is, there exists such an element in this polynomial ring such that this is equal to the zero polynomial. Okay, that is the definition of an algebraic function. If such a p exists, then we say that f is algebraic. And if no such p exists, then f is called transcendental. So it's just mentioned in the passing that this notion of algebraic and transcendental functions, but it's not our primary interest to see what they have about them further, any further than this. And then the author of course also mentions that we have in fact come across some more exotic functions which look very, what can I say, somewhat very strange, that it's the rule for the function itself is very strange. For example, this function. This function maps every rational number onto 1 and maps every irrational number onto 0. We use this function every now and then to create counterexamples to some things, some statements. Now, if we are given, now let us see a new notion, which is actually not new, but still let's just see it. Suppose we have a function from R into R, and suppose X is a subset of R, then one can consider this function. Its domain is X and range is R, and it is defined like this. In other words, what we have done is we have only replaced the domain R with the subset X. That's it. We have not actually essentially changed the rule of the function also, because you can see that the value of this function at X, when you evaluate it at X, by definition that is just the value of f at X. So the difference is only that now our inputs are coming from X. They are restricted to come from X instead of being allowed to come from the entire R. And this is called the restriction of f to the set to the subset X. For example, if you consider the ordinary square function, which maps every real number onto its square, then you can consider the restriction on the closed interval 1, 2. It will then have this interval as its domain, R as its range, and what it will do is just simply this. And this is not the only way of restricting a function, that is by restricting its domain to a subset of the domain, but one can restrict the range as well. However, one has to keep in mind that here also you can take a subset, but all the function values must be contained in that subset, otherwise things will go wrong. For example, to see that, this itself can be restricted by changing the range. That, however, is not called the restriction. Okay, whenever we say the restriction of a function f, normally that always means that we are restricting the domain. But if we restrict the range, then also we get a new function, but that does not have a name, any name to it. We know that the square of any real number is a non-negative real number. So from that fact, we can restrict this function in this way. If you want, you can give it some other name also. And actually we do not run into any kind of problem or any paradox, because here all the non-negative real numbers are available in the range. There also we had all those numbers, but Additionally, we also have the negative real numbers, which do not appear as images of any real number under the squaring function. So if you discard them, then also there is no problem. Now you may notice that we have just simply named this function the same f, and it seems that there is no problem. Why is there no problem? Why is there no problem in calling this other function also f? We feel like that because the function essentially, these two functions essentially do the same work, that is, they square the input. And also the difference that you had here, namely here the inputs, or for example here the inputs are restricted to come from this subset. That restriction is not here in this second situation. Here also the inputs are allowed to be all real numbers. Here also the inputs are allowed to be all real numbers. And the outputs are there. Here also all the outputs are there. But simply because the ranges are not the same, so technically these two functions are actually not the same. But still, we say that they are the same because most often we are concerned with the values of the function rather than where those values are lying. They are real numbers, they are non-negative real numbers, that's enough for us. However, sometimes this will be an issue. For example, this function, just for a moment, let me just call it, say, f1. Let me give it a new name. You can see clearly that f1 is onto, but f is not onto. So if you are discussing ontoness, then the distinction is necessary. But if you are just interested in studying the values or how the function behaves as a rule, then there is no need to distinguish between the two. And in fact, we ourselves will not be very careful in distinguishing between these two things, unless something goes wrong. We will see from the situation, from the context, if that can be done, or if we will run into a problem. It will not be a big issue if we do not be so careful. We can afford to be a little careless. Now, you see, so far we have been doing all the things analytically, that is, using properties of real numbers and those things, or in other words, we are not using geometry to prove anything. That can also be done rigorously, provided we know the axioms of geometry, which we do not do, we won't do in this text. That's what the author says. However, we should not forget entirely about geometry. That's because, you see, whenever we think of a situation or something like this, usually if we can draw a picture, then looking at that picture, looking at that figure, everything can be seen at once. And that aids in our understanding. And for functions also, there is a figure that we take the help of. And in fact, we are well familiar with that. That is called the graph of a function. So one can rigorously define the graph like this. Say you have a function f from x into R, where x is some subset of R. the graph of f is defined to be the subset, this subset, subset of what? Subset of the plane R2. And when we say subset of the plane, that means there is an underlying geometry, and using that geometry one can see what the function values are doing at once. You see, most often the kind of function that we are interested in analysis will have infinitely many values. Okay. So sometimes thinking of them analytically or as a for example, here also we are just simply saying that the graph is defined to be this subset of R2. So you may choose to not think of anything geometrically. That is up to you, but sometimes if we think of it geometrically, for example as a curve or something else, then it will only help you. Okay, it won't cause any problem. However, we have to keep in mind that we use that only as a tool for better understanding, not as a way of proving something. You can do that, again I am repeating, provided you use the axioms of geometry rigorously, specifically geometry of the plane R2, and we won't do that. Now one may of course ask, then why are we doing this? I mean, is it not somewhat unintuitive to always work with things analytically? The reason is that as the number of variables increases, once you go beyond 3 variables, your geometric intuition starts to fail. For higher dimensional spaces also there are geometry in a very specific sense. Okay, I am not going to discuss that here right now. But the rules for those things are, we are not very well familiar with that kind of geometry. So our intuition starts to fail us in such situations. That's why we take the analytic approach, so that using the analytic approach, whenever the need comes, we can switch from one variable to many variables, and in fact potentially infinitely many variables. And now, after having this little discussion, we come to the only definition of this section. And in this definition, we define arithmetic operations on functions. We already know arithmetic operations on numbers. In fact, we have devoted so much time developing all the number systems up to the system of real numbers. But we can do some such similar things with functions. Again, using the arithmetic of operations on numbers themselves, we are going to do this. I mean, we won't have to go through all the hassle of developing number systems again for functions, nothing like that. So let's see the definition. Let X be some subset of R, and let F from X into R and G from X into R be functions. We define the sum of these two functions f plus g, their difference, their maximum, minimum, product as follows. There are two other things that will be defined, but we will do it afterwards. The definition is as natural as things can be, absolutely straightforward, and similarly we have these other operations. Then maximum of f and g at x it's defined to be equal to the maximum value of f of x and g of x. Similarly mean, and then product. Now let's just take a moment and see what it is. Okay, what is it that we have defined? What do we mean by f plus g? Actually, from these definitions we can see that just like f and g, f plus g, oh I forgot to mention one crucial thing. For all x belonging to x. Okay, otherwise this definition is meaningless. Now where is x coming from? X is coming from here. So you can see that this function, for example, yeah, I have already said it's a function. It's this sum itself is also just like f and g, a function from x into r. Why? That's because when we are taking an input from x, then we are getting an output. But keep in mind, we still have to somehow make sure that this f plus g is a well-defined function. Is it? For that, we require that every input x coming from x gets a unique output in R. Is that the case? So you are taking x from x. Okay, fine. F and g are well defined and they map, each one of them maps x into R. So this f of x and g of x are unique real numbers because of that fact. For a given x, these two are unique real numbers. So their sum is also a unique real number because the operation of addition itself is well defined. So that's why for a given x, you are getting a unique real number, which is this, and that is this function f plus g. Similarly, f minus g, max, mean, and product, all of these are functions with domain x and range R. Now let's go to quotient. If g of x is not equal to 0. For quotient, this requirement should be there for all the inputs coming from x. Then we can define quotient. When we define this by this rule, so because of that appearance of g of x in the denominator, all of this need to be non-zero. So you can go back to that example where we have this, no? You can see that this f is actually, just for the sake of clarity, if we give it another name, say h. This h is actually f over g, where f is the function that maps x onto 2 to the power x and g maps x onto x square plus 1. And this can be formed because x square plus 1 is never equal to 0. For no real number x is x square plus 1 ever equal to 0. In fact, it's always positive, and that too greater than or equal to 1. But anyway, so this is one example where h is actually the quotient of two such functions. But there is one more construct. For any real number c, we define the product of c and f. It's like you can multiply a vector or a matrix or any such thing by a scalar. Just like that, you can multiply a function by a scalar, and that again, like all these constructs, will be a function itself whose value at the real number x is just the product of c and the real number f of x. And you can see, it's not very difficult to see that this is a special case of the product, where in place of f, of course, you have f, but in place of g, you can imagine the constant function which maps every x onto c. From that itself, you get this, and that is just the definition. Actually, this definition is going more towards algebra than analysis, but we won't have anything more to do with this definition other than the fact that we will need these operations every now and then. So that's why we have it. And to illustrate this, there is an example also. So let's see that example. Both algebra and analysis as well as topology have to be simultaneously considered when one studies functional analysis. At some point we will do that, but we will need to go through real analysis first fully, and also a bit of complex analysis. Then only we can go to functional analysis. And for functional analysis, we would also need linear algebra, which we are yet to see properly. I mean, we have already seen vector spaces a little bit, but we need to know the theory of linear transformations. So let's see the example. Consider the functions so f is the function which maps every real number onto its square, and there is this other one g which maps every real number which doubles every input. One more fact that I forgot to draw your attention to, that is, before adding or subtracting or applying any such operation on two functions, make sure that they have the same domain, otherwise things may become meaningless. For example, if your x does not lie in the domain, that is the domain of f as well as g, then one of these two values will become meaningless. So your function collapses. And even when they do not have the same domain, for example, you have said this. Suppose f is some function whose rule we are not saying what it is, but its domain is the closed interval 1, 3. And say g is the function whose domain is the closed interval 2, 4. Then of course you cannot just simply define f plus g as it is. But you can still do something. You can restrict both f and g to the common domain, means the intersection of these two domains. That is, you can restrict f. What is the intersection? It is the closed interval 2, 3. This restriction you can consider. It has this interval as its domain. Similarly, you can also consider the restriction of g to that. And now the domains are the same. So now you can multiply these two restrictions. Okay, that way you can combine them. Now for these two functions, of course, f plus g is x square plus 2x, f minus g at any input x is x square minus 2x. But let's also see what fg is. Fg will be f of x times g of x. So ultimately it gives us 2x cubed. Now you see that these two functions can be composed also using our usual composition of functions in two different ways. I mean, in both the ways. F composition g will be what? Let's see. First you apply g to x. Doing that you get 2x. On that you apply f, which means you square 2x. That is, you get 4x square. Similarly, if you calculate g composition f, then you will get 2x square. And you can clearly see just from the look of these three rules, or by putting actual values, that these three functions are distinct. None of them is equal to any other. So while composing two functions or while taking product, you should keep in mind what they are. They are not the same thing. But when we are not careful, we may easily forget this distinction. And with this section itself actually ends. There is only one exercise which I won't solve today. We will do it the next video. And that's just it for tonight. See you in our next update, and the next upload is when this coming Tuesday. And on Tuesday, let's just instead of again starting with group theory, let's just go to vector spaces. Actually, we are in modules right now, so let's just go back to that on Tuesday. And that's it. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.